Now notice that we took a lot of interest in the bus architecture when we were talking about the DMA controller. And you can see here that the interrupt, which kind of shows it on the bus, really isn't on the bus. The interrupt lines are on their own separate lines. They're not part of the bus architecture. Whereas the data transfer is definitely on the bus architecture. The status word for the completion of this operation might be on this bus, or it might be on a specialized bus that the CPU and the DMA controller share, which is what most architectures have today. The implementation is up to that particular board designer. Any of those combinations will work, and all of those combinations have been built at one time or another on different machines. That part isn't really important to us from an operating system's perspective. What is important is the functionality. And the fact that when we start talking about DMA controllers, we definitely have to have a bus architecture instead of specialized interfaces between components, because at any point the CPU could, depending upon how you programmed it, the CPU could take over the transfer operation and still do the I/O. You can still put it into program I/O mode. You can still put it into interrupt-driven I/O mode. You can also take advantage of the DMA controller and let that handle the transfers. So in this bus architecture, you can do any or some combination of the three I/O techniques. And it's going to be based upon, again, what that job is that you're trying to write the software to do. That make sense? Questions? Another thing that's, I think, helpful at this point, too, to understand. Did I put that slide back in here or not? I don't think I did. Okay, so we have our processor subsystem. Just do it this way. Our memory subsystem. And of course our I/O subsystem, which is really, really important. Because that's the chapter, right? Okay. So depending upon what I/O device I'm going to, say a keyboard, remember in chapter 1 we talked about the fact there was these different standards, these different protocols for different types of I/O devices, right? Sound familiar? I got 3 yeses. Isn't great. Okay, remember we had we have a number of different I/O standards that's going to define electrically what this looks like, but it also defines the protocol that the data transfer, as well as the electrical handshaking between this external device and the computer device is going to do. In order for us to implement that, we have to have some hardware on this side that takes those electrical signals at whatever voltages and whatever rates they're running and creates bytes out of them, right? And the stuff that we talked about at the beginning of this chapter in a meaningful way, in some cases encoding even. Okay, so anybody know what these devices are called?
Drivers.
We might use a driver to program them, or it's better stated, to, it'd be better stated if I remember the word, to transfer its hardware signals into assembly language, right? But we still have to do that part. So what devices do we, all right.
Controllers.
Who knows what that means?
Or UARTs.
Yeah,
Universal
yeah.
asynchronous.
Universal asynchronous receiver transmitter, otherwise known as a
Signal communication.
serial chip, right? Serial, it's for serial communications, but this is a chip, right? And this chip knows how to translate, that's the word I was looking for, knows how to translate, something that says 01000 means to initiate transfer, right? It knows how to translate those things. So my device driver is going to say, hey, if I want to initiate a transfer on RT in assembly language, then it's going to generate from RT a 010000. So that this UART device or chip can generate the correct electrical signals at the correct voltages to transfer the byte through. This is review, right? 237.
100%. I don't know. It's been
What's
too long since
237?
237. It's like machine over
Machine, yeah.
I don't know if we.
Don't think we did that.
I can't really say that we discussed it or not.
That was what, 5 years ago, 4 years ago?
Well, 3 years ago, but
Okay.
Do you guys actually use it, or you just touch upon it?
no, we actually write all the packages in a complex instruction set.
I mean, you are serial
I mean, I've used it on Arduino, but
Mhm.
I've used the serial interface, but I didn't know it was part of the firmware, but now I do.
Yeah, you do. So that's just one. So we have these chips here which are translating specific protocols to electrical connections that devices can connect to according to those protocols, right? So the reason I want to revisit that, make sure we understand it, because I understand the I/O subsystem, you have to understand that it's doing everything from talking about your code that you wrote to say get byte, put byte, read, write, whatever, down to these voltages that can be understood by these devices, okay? And it takes some other components that we need to be mindful of, we need to be aware of, because that's all part of when we start writing device drivers, what we need to know, okay? So in order for us to manage this, in order for us to get from a read or a write to an RTGT or whatever, I am going to need an additional component. An additional component could be, it could be here where I have maybe a bunch of UARTs, maybe I have, I'm getting ahead of myself. In this case here, I am going to need something called either an I/O controller or an I/O processor. Let's start off with I/O controller first. Because what the I/O controller is going to do, and it's really part of the I/O subsystem, but I didn't draw it fast enough. Because what the I/O controller is going to do is it's going to translate a lot of the RD into timing sequences and electric timing sequences mostly, as well as any other conversions, such as if you're doing some character formatting for a human readable device. It's going to do that processing before it gets to here. So turning on, knowing how to turn on a UART chip, knowing that pin 3, I think it is the one to tell it to turn on and tell me if I have the device, right? It does that translation, so I don't have to try and build that into each one of these individual chips. I have one I/O controller that can talk to my 3 UARTs, my 3 serial ports, and it can do that for us. Okay? And there's others. There's others. Well, I could mention the I/O processor. We'll get into that later because I do have slides on that. But that's the purpose of breaking these down, so you can understand where the work is being done, because this work has to be done in order for us to do an I/O transfer. The idea being is that we want to, just like our virtual processor, just like our virtual memory system, and our virtual I/O subsystem, we want to not only virtualize this as much as possible, but we're also creating as much abstraction as possible. Right? We're creating an abstraction so that we can use a simple open or write system call to do all this work with. And then the translation of, oh, an open on my thumb drive is different than an open on my CRT. And it's open, it's different on a modem, right? Let's do that translation down as low as possible. And let's create that layer of abstraction here that we could then program with much more efficiency. Make sense? That's kind of our goal here. Yes?
So IOC, the one that know which one is keyboard, which one is USB, which one is thumb drive.
So when I have the address of the device, that will have the address of specifically the keyboard or the mouse or whatever. Okay, so that'll get passed through with the open system call. So I will have the address for each of these devices when I do that abstract open system call. And what the IO subsystem will do is say, oh, this is the address for that device. Well, that's really a 0x12 or whatever. Pass that on to the IO controller, which can then raise the right signal level for whichever one's OX12. Make sense?
Is the address that is it the address created inside the IO virtual?
No, it's created by the operating system.
So when you plug it in, right, that's when you.
Yeah, depending upon which of these devices you plug into, each of these devices have an address.
Okay.
And this IO controller knows that this is address 0x12. And then, that way when you want to go open it, that's defined by this operating system. When the operating system creates itself in memory, one of the things it's doing is it's going out to the IO subsystem saying what devices are attached at which addresses. That way when you at an application level or system level, once you write something that opens up the keyboard, you know which one to use. And you can use that same system call on a machine that has keyboard plugged in here, or plugged in here, or plugged in somewhere else. Great question. Other questions? Okay. All right, so let's dive down into the DMA a little bit more detail. Okay, so it has these 4 components to it. Obviously, the control logic is going to be important because that's where we can request the DMA controller, the DMA can acknowledge it, where you can initiate a read, where you can initiate a write, and of course where you can raise interrupts. Those are control signals, and there's others. These are the very basic ones, and sort of the minimal set, if you will. Other DMA controllers have some additional bits for different capabilities that are built into it. But at a minimum, it's going to have these things. And notice the language I used, right? Where DMA request, the arrow pointing out, meant that the CPU can request the DMA controller. That's what that arrow says. Whereas the DMA controller is going to acknowledge it, shows the line coming in because that's the source of that signal. Okay? Address register. This is where buses get to be fun for your science students. Because what happens when you're forming an address is you're actually enabling the lines, and it's typically a matrix. I think I touched on this when we talked about memory in buses in the first place. But that's right, they took part of my board. That's already spoiled. I can keep erasing, that's always going to be ugly, so let's go here. So use black, will be a little easier to see. Yeah. So here's my DMA controller. Here's my CPU. Here's our memory. And they're all interconnected on these buses. And as you might recall, we showed that we can have a very simple single bus, or we can have a complex collection of buses. You might remember that? So in this case here, I might have I will have a need for both my DMA controller and my CPU to touch data, memory that has data in it. And so what I need to do is I need to have some electrical signals. I'll show us 4. That allow me to get to any of these lines. I know, I'm supposed to show a little humpy things. Okay, so that allows me to raise specific addresses in main memory. So by having these on the bus means they are really together on that same bus, sharing those actual electrical lines with those actual electrical lines in memory. And so timing is going to be critical. And we have slides on this later, but I'm just introducing it now. We're going to talk more about this later with the clocks and stuff. But timing in my system is going to be absolutely critical. It's because I might define portions of this time here where I'm setting the address lines versus using these data lines. So this bus here might be part of the cycle, it's an address line, part of the cycle, it's a data line. I might have separate buses, so I don't have that problem, but some architectures, they're splitting that function. So what that means then is at the right time, if the CPU is trying to get to a memory location, it would raise the right bits to get to whatever that address happens to be, and then it could read that or write to that location. Okay? DMA controller, we want it to have that same capability. We have to worry about collisions though, because we said this is another processor, right? So it's running now asynchronously with the CPU. So we have to think about our bus design in more detail. We will later, when we start to realize the fact that, hey, if we're both working with the same memory and we're sharing the same data lines, we're going to have to worry about collisions. Okay? I'm not going to try to solve it here right now. We're going to come back and revisit that. So keep that in mind, because I'm not going to draw the picture here. Make sense? Okay, but that's what they're doing. That's what we show, address lines and data lines. They could be separate, or they could be shared like this. Originally designed for like this. Most systems today, I have separate lines because I don't want to have to worry about solving this collision problem. And I want the stuff to move faster through the system. I'm still going to have the potential for collisions even if I separate these lines for reads and writes. Right? So if this was strictly my address lines, I still have to worry about both of these trying to raise the address lines at the same time. So I'm still going to have to split my clock cycle between the two, or some technique like that. Okay, so I need to form the address so I can then transfer the data. Does that make sense? And it's not graphically. I didn't draw the separate bus lines for a separate data bus, but you have pictures of that in the system. Oh, I did put this one. I didn't put the other one. Okay. All right, so let's go ahead and talk about the different bus architectures a little bit then. In this case here, we have the case of, we have our main processor, we have the DMA controller, and we have a whole bunch of I/O controllers. Okay? It says I/O there, but that's what they are. It's a bunch of I/O controllers. And main memory, of course. So in that case there, it's very much like that diagram there, where I'm raising address lines up. It could either be the DMA controller or the CPU, and then I have to worry about making sure that only one is reading or writing, right? On the same lines as the address lines. That's what that shows. Now, we could say, let's solve the collision problem by taking the DMA controller and integrating the I/O controllers directly with it. So that way I don't have to worry about using at least that same bus between the DMA controller and the I/O devices, right? So we have different ways we can do that. We can have a single I/O controller attached to the DMA controller, or I can have a DMA controller with multiple I/O controllers. This implies one of two things. Either I have a whole bunch of DMA controllers, which is a really bad idea, or I have only one I/O controller, which is also a really bad idea. So I've only known a couple of systems that had this architecture here, and they were mostly experimental systems, so you don't see that too much, but we did see this quite a bit. Where we had multiple I/O controllers, all directly connected to a DMA controller. Specifically, what they had is just sort of a mini bus sitting right here that the DMA controller can talk to the I/O controllers with. Downside to this approach is that the DMA controller has to move memory content for all of the I/O controllers it's managing. Okay. The upside is you don't have collisions. You don't have collisions because it's just the one DMA controller. So then we evolved into separate buses for the I/O subsystem versus the CPU or the system. And this was a very powerful and long-lasting architecture that really sort of allowed us to do true multi-programming systems. So even back in late 70s, we had some machines that were coming up with this kind of bus architecture and coming up with some pretty powerful computing capabilities. Where we had one bus, which main memory, DMA controller, and processor all communicated through, so it allowed the processor to mostly have access to the main memory. Okay, but the DMA controller then had all of the I/O subsystems on a bus, no longer a mixture of things here, and then it then managed over the bus the different I/O controllers. When you see these I/Os, they're really IOCs. Okay, now we still have the same problem where the DMA controller is still moving all of the data from memory, but now I have integrated buses everywhere, so I can insert, remove I/O controllers as needed without changing the architectural design of the system. That was a very powerful change in architectures at that point, like I was saying, late 70s, early 80s, where we were able to start making some pretty powerful machines. Okay? There's still some downsides to this that we overcame because we still have all data going across the system bus. That's kind of one downside to this. And in modern systems, what we usually do is we usually have, you don't see this as much because everybody now does it, but you used to see vendors saying, I have dual ported memory I can sell you. It was a big deal. DIMM chips even. Dual ported memory. What dual ported memory did is it allowed us to connect the DMA to the other side of memory so that the CPU and the DMA controller can both simultaneously access main memory on their own buses. No collisions. Unless, of course, they're trying to get the same address location, but dual ported memory solved that problem too with interrupts. Okay? So in pseudocode, what did this look like then? Pretty straightforward. Copy from user, we move the data from user space to kernel space. Initiate the DMA controller, that's passing in all the control signals, right? Remember the three things it passed? Starting address, number of bytes, or size. The third, the handshake word, right? Whatever that handshake word is, whatever the ready is, whatever the signal that has to set to get the device is. It passes that to the DMA controller, those three things, we just call scheduler, or goes on and does other things. For the process, just have to now acknowledge the interrupt, unblock the user, turn from interrupt, simple. Questions? All right, good place to take a break. Let's take 10 minutes, and we resume about here after 25 after.